conflict. That is two instructions which are on the pipeline in the same cycle is trying to use the same resource, and therefore there is a conflict. So two instructions at the same time cannot be in the decoder or in the execute and so on. So there are different resolutions available. First, for the correctness of correctness due to all different hazards, we have a hardware mechanism of stalling the pipe, which by which it means that the next instruction, which had to execute on a certain at a certain cycle at a certain stage, is delayed by doing a no operation or NOP. And there is hardware provided in the pipeline so that in case the code generator misses to avoid this conflict, then the stall will insert these no ops to maintain the correctness. Naturally, that delays the program execution and loses on the benefit of the pipeline. We can have more resources, we can replicate resources, different types of ways structural hazards can be resolved. Then we looked at data hazard, which we have also seen that it's a data conflict because of data dependency, which can result in race condition or also called race hazards. Now, it may be of three types as we saw. It's basically the most critical is the read after write. A data value is being written to some register and a later instruction reads that value called raw, which is a true data dependency. And we have two other kinds of data hazards also that we discussed. What is write after read, which is anti-dependency, and write after write, which is output dependency. And we noticed that both war and wow can actually be resolved by renaming, having more registers, renaming, writing to different output registers. So therefore, they are of less evil in that way. But raw will have to be resolved. So again, the resolution could be by the hardware. In that case, the hardware has to do two things. One is it has to detect that a read after write is about to take place, which it can do by looking into the different pipeline stages and what are the data values available at different stages, and then stall the pipe accordingly. Insert NOPs, delay the execution of further instructions till the required data is available to be read after the write has completed. This naturally again delays and slows down the pipeline. The second that we have discussed is a special hardware for forwarding and bypassing that is provided in the pipeline. So the forward or bypass works on the principle that it's when I need to read something from a register, I may not actually wait till that register is written back. Internally in the hardware, that result may have got generated. I mean, certainly will get generated before it is written back to the register. So if I'm doing an ALU operation, after the execution stage completes, even before the subsequent mem and write back, it will be available in the ALU. So we can do a bypass from that point to the required instruction where the read of the register was supposed to be done. The same thing can be done in case of load instructions also, because load actually the memory value is obtained in the mem cycle, and we do not need to wait for the write back to the register bank to access it. We can directly bypass and get that value in the required instruction. So forward and bypass is a hardware supported mechanism which can be exploited to get a better throughput and decrease the number of stalls. War and wow can be resolved by renaming, as we saw. And then we saw that after with all this, we can schedule the instructions in a way so that some of the stalling cycles that will otherwise happen can be used by later instructions which do not have this kind of data or structural hazard happening there. So kind of we change the sequential order of the instructions to utilize the stalling cycles and get a better throughput. We have done a complete workout with different kinds of combination of stalling, forward bypass, and scheduling to see that how we can get almost near optimal throughput in terms of data hazards. So this is what we have done so far, seen so far. Then we have discussed about the control hazard. Control hazard is a control conflict which happens when there is a branch instructions. Since if we have a branch instruction, naturally at the point of branch instruction, already several other instructions are waiting in the pipeline to be executed. So if the branch is taken, that if after that condition check, if we are actually branching to the target instruction, then the instruction already executing in the pipeline will become invalid. And otherwise, if it does not take, then we will continue in the same way. So branch, first effect of branch is to stall, because you cannot certainly, because you do not know whether you will continue with the instructions in the pipeline already, or you will have to load some other instruction. So the first thing is you stall, put no ops to make those decisions. And if the branch is taken, then you will have to do a zap or flash, because instructions already in the pipeline are not to be logically executed. So you'll have to remove them. So it has a pretty high cost in terms of the pipeline. So how do we resolve this? This is, stall and flush ensures correctness of execution, of course, supported by hardware. The hardware also has forward and bypass, which we can make use of to make decisions faster. But what is interesting is many pipeline architecture provide a delay slot. A delay slot could be of one cycle or could be of multiple cycles, which says that after the branch instruction, or rather when the branch instruction is actually executing, during that time, instead of totally stalling, you always execute the instruction immediately after that, irrespective of the outcome of the branch. So naturally, it has to be an instruction which is not dependent on the decision of the branching. So delay slot is provided for that, and that has to be naturally filled up by the compiler by putting an instruction which in any case will be executed irrespective of whether the branch is taken or the branch is not taken. So we can exploit that in the code. And finally, we can do again different kinds of instruction scheduling, rearranging them, and we can do speculative execution. So going to the next slide, this was a simple example that we illustrated where BEQ, branch on equality, is on success. If R1 and R2 are equal, so it's supposed to branch to L, which is at 0x1c. So already at that time, already add and sub would be in the pipeline. They will first be stalled and subsequently zapped if the branch is taken. Right? So this is the basic problem we are trying to address. So the compiler strategies will that we are going to discuss will be of two categories. Combination of two things. One is instruction scheduling. In instruction scheduling, we will try to exploit the delay slot, assuming that at least one delay slot is there. We'll try to show how delay slots can be exploited. And the second, which is very interesting, is when does, we are just asking when does branching affect most? Now, branching grossly, as you can see, could be due to just a simple decision if else kind of decision being made. You either go this way or that way. Or, which is very common, is when we have loops. So branching is every iteration of the loop needs to decide based on the iteration variable or an expression based on that as to whether it should do the next iteration, or it should conclude that the loop is over and it will go to the next logical instruction. So as many times the loop iterates, the every iteration will have such a branch decision to be taken. So the basic idea of unrolling is, if we can unroll the loop, and we'll see how, what does under what conditions we can unroll and what does it do, which is basically, instead of just doing one iteration at a time, if we make a loop which does two iterations of the original loop into a single iteration, and therefore with this transformation, with this unrolling, it does half the number of total iteration, and therefore the number of branching requirements become half. So we can unroll for more iterations also. So that is one way to get to two things. One is, since as you unroll, the number of branching goes down, so your basic origin of control hazard reduces. So that is one advantage. The other advantage is, in a single iteration, you have a lot more instructions available, which can be rearranged to exploit the delay slots and utilize to make effective use of the stalls and so on. Right? So this is what you will see. The other strategy, which is often combined with this, is called speculative execution. That is where you say that, well, even though, particularly if you look at branches in a loop, certainly you would expect in a loop in general that the branching to check condition for termination will actually resolve for continue in the next iteration most of the time. It's only once that it will actually come to the terminate branching. So even though the branching has two ways to go, one of the ways, which is uh, branch taken or branch not taken, depending on the way you write the condition, one of them will have much higher probability of being taken than the other one, right? So can we make use of this probability? Now the question is, this depends. You will argue that this is not statically resolvable. Of course it is not, because if I do not know the data, I do not know how often the loop will continue and how often it may terminate after just a few iterations. So this also means that alongside the static generation of the code, we create some profiling code, some instrumentation, so that we can collect statistics of how the branches are being taken. And based on that, at the runtime also, we can have some clue as to which one should be done more, or we can do it across, different executions of the program, collect data by running the program for say 100 times with typical data, collect that statistics, and then based on that statistics, re-optimize the code and then run it. So that comes under speculative execution or branch prediction strategies. Okay. So we will first discuss about the loop unrolling. Now, first thing in loop unrolling that the compiler has to decide is whether the loop unrolling is useful. Right? Unrolling every loop may not be useful. So for loop unrolling, we would mostly need to decide whether the loop iterations are independent. We need to determine address offsets for different loads and store, because as you unroll, suppose you are accessing an array AI, right? So you know that the actual offset for that is 4 star I, right? If it is an integer array with every integer having size of 4 bytes. Now, as you unroll the loop, you will be accessing AI as well as AI plus one in the same iteration. Therefore, you will need to have different offsets and appropriately computed so that you can load that value or store that value and so on. Naturally, since as you unroll, you are repeating instructions, so your program size increases. So it has some cost in terms of the program size increase, which in some cases may have some detrimental effects. The second point is, as we saw in terms of, say, WAR or WAW, and we will see that as we unroll loops, we want less dependencies. So the basic requirement of registers go up because unnecessary constraints, which are basically anti-dependency or output dependency kind of constraints, can be removed by not using the same register for different computations. If you can give them different registers, then you will have much less dependency on that, much less possibility of data hazard, and therefore your computation will become faster, your pipeline will become faster. Obviously, the flip side is it has a stress on registers because, as you know, the registers are limited. But you'll see, I mean, this is one of the reasons you must have been told in the architecture course that this is one of the reasons that risk in general and risk with pipeline normally are provided with relatively larger register banks compared to the earlier processors. Now, the other points that we will need to take care is if there are extra paste and branch instructions, if we can eliminate that, we can adjust the loop termination and iteration code appropriately for that. We'll see examples of that. Now, let me introduce two different terms here. A loop may have dependency within one iteration only. It may have dependencies of values just within one iteration. So if a loop has that, then you can see that two iterations of this loop are necessarily independent, right? So they are considered parallel, right? So multiple iterations can be executed together as long as you maintain the order within one single iteration, right? So that gives you more flexibility to move around code. The other is a loop may have dependencies across iterations, that what you compute in one iteration, you use in the subsequent iteration. Then it is not parallel. And these dependencies are called loop carried. And we will see how unrolling could be used to remove loop carried dependencies and create loops which are purely parallel. Okay? So these are the basic points. Let's start with examples. So here you can see these loops are not related. These are just 4 examples put in one slide. So let's say you have this first instruction. Right? And before I go further, you'll note that in most of these examples, we use loop count as constant. Right? Because if the loop count can be constant, then you get much better better option to optimize the loops. So in many cases, actually, where this becomes more useful is when you deal with vector matrix kind of operations, where certainly the loop count is not significantly variable. Right? So we do not lose much by considering that the loop bounds are actually constants. So look at the first example loop. In that, xi is an array and s is some value which is loop invariant, right? So far as the loop is concerned, we can assume that s is a constant, right? So we can just have it in a register and keep on using it. And you can see that there is as such no dependency at all, right? There's only one computation, whatever. So I can actually, if I had the hardware, I could have done all of these 1,000 locations I could have done in parallel. Right? So there's no dependency as such. Look at the second one. In the second one, I have two primary arrays, A and B, which are affected by the loop. I have another array C, which is used in a read-only mode. So what if you look at the first instruction here, say S1, then what will you say that when I'm computing for I plus 1 in the loop, then I am actually using the value of AI, right, which has been computed in the previous iteration. Right? So I say that S1 actually depends on itself from previous iteration. Right? It depends on that value computed. Right? If I look at the next instruction, S2, then again, BI plus 1 depends on BI. So S2 depends on S2 from previous iteration, that is across the iteration. And if I look at BI plus 1 is using AI plus 1. So in the I plus first iteration, S2 depends on S1 in the same iteration. So this is the same iteration dependence, and these two are dependence across iterations, loop carrot kind of. Let's look at the third, which is, you can see that AI depends on, computation of AI depends on BI. So if you consider the I plus first iteration, then you are actually having to use the value for from the previous iteration as computed in the previous iteration. So S1 actually depends on S2 from the previous iteration. S2 has no dependency because it is using two other arrays which are in the read-only mode only. The fourth and last example, you have xi computed from xi minus 3 plus s, very similar to the first one, but because you're referring to three values prior, so S1 actually has a dependency on S1 from three previous iterations. This is often referred to as recursion in terms of loops, and the dependency distance is 3, which significantly limits the option for parallelization. Right? So these are different examples. So what we will do, we will take one of these and illustrate the basic process of loop unrolling and how does that help in removing this loop carrot dependency. So we are taking the third loop example here. So a loop carrot dependency, we are assuming that there is no cyclic dependency, that is S1 depending on S1. In the absence of that, the loops can be restructured to be parallel. So this is what we have. Right? We have understood why S1 depends on S2 from previous iteration. Right? Now you take a look at the code below. What I have done here, I have basically unfolded the two instructions, one after the other. So what will happen in iteration 1, the magenta comment, I will have A1 and B2, these two computed. What will happen in iteration 2, the green comment, A2 and B3 will get computed. What will happen in iteration 3, A3 and B4 will get computed, and so on. In iteration 99, A99 and B100 will be computed. And finally, in iteration 100, A100 and B101 will get computed. Right? So this is, if I, instead of writing a loop, if we could just write all of these as consecutive instructions in that way. So putting 200 instruction, and each consecutive one, starting from the first one, 2 consecutive instructions are one iteration of the loop. Now what I do, I regroup these instructions. The order remains same, but I just regroup. So I say I leave out the computation of A1. which is done only once. So then I compute, I group the computation of B2 and A2. So see, the what we are getting here by doing this is, earlier in the same iteration, I was having to deal with both index 1 as well as index 2 for the arrays that are being computed, that are for the array elements that are being changed. When I do this, change the grouping into the blue pair, I have only dealing with the value 2. Don't worry about the value 1 for C1 and D1 because they are just read only, so they do not provide any dependence. Similarly, if you look into the next pairing, the one shown in red, I have only values dependent on 3. In this way, finally, in this last blue one, B100 and A100, it is only on 100. And that will leave out one instruction, which is computing B101, which is I keep outside. So I have one initiating code assignment to A1, which I put outside the loop. I have one post termination code, which I put outside the loop. If I take these two out, then I'm left with 99 iterations. Okay? So I run it from 1 to 99, and I have naturally adjusted the index according to that. So for the first instruction, AI is equal to AI plus BI, I have made it AI plus 1 is assigned AI plus 1 plus BI plus 1. Now, once I have done this, you can see that now the dependence is only on BI plus 1, which is from the same iteration. So S4 depends on S3 in the same iteration, but the earlier feature that S1 was depending on S2 from previous iteration is gone. So the earlier loop, which was loop caret, which has loop caret dependency, now becomes a parallel loop, and it's more amenable for optimization. And two, initiating and terminating instructions are taken out of the loop. So this is a very loop unrolling in this way is a, I mean, it finally here, the unrolling is logical, as you can see, because we have not written it in the unrolled form in the final loop. It is exactly in the same way of iteration, but the unrolling has given us the insight to reorder the instructions and adjust the indices, which makes it parallel in terms of execution. Right? So this is the first purpose of loop unrolling, which we can then use for different optimizations. So even though a loop may have loop caret dependency, by using this technique of loop unrolling, we can transform them into parallel loops, and in subsequent optimization, we can assume that the loops we deal with are significantly parallel in nature. Okay. So before I go to the next example and actually show how optimization in pipeline would help from this, let me just get back once to you to see if you have any questions up to this point. Any questions, friends?
Yes, sir.
Yes, please.
So in loop unrolling, so the basic optimization that we are getting is just due to parallelization.
Parallelization in terms of the possible computation. Now, it depends on the architecture and other constraints as to how we exploit that. There are two things that you have to understand. One is you make the option to run more instructions in parallel. You try to drive minimizing the dependencies. And the second is, once you have that, how do you use it in your optimization? Getting that? So it is not necessarily always that if I have converted a loop carried dependency into parallel loops, it may not be for all loops. A MIPS 5 pipeline architecture may not be able to exploit a lot more, but it makes it easier, of course. But if I have say a superscalar pipeline, I will have a lot of benefits because I can take multiple iterations and execute them in parallel. Right? So it is not always the techniques are not just one-to-one, because since we do not have enough time left for discussion, so I'm not being able to take up a whole lot of different architectures. So I'm talking in the context of one pipeline architecture, in which some of these techniques will be useful, but I'm trying to cover the techniques little bit and more generality. But the basic point is, you first try to devise techniques to minimize dependency in the code. You try to devise techniques to minimize branching in the code. And then you see, given your architecture and the different constraints that you have, how much you can generate a code which is optimal. Right? Does that answer your question, or did I answer something else?
So somewhat I get it.
Right. So I mean, I get that what you're asking is, we are working for optimizing for pipeline. How do I benefit by making things parallel? Right. So it is. We may in some cases gain, because as you make iterations independent, naturally the actual physical unrolling of the loop becomes easier, as we will see. But certainly we will get significant benefits if you actually have a parallel, superscalar or VLIW kind of processors or things like that. Right?
Yes, so.
Any other question, friends? Thank you, Vilash. Oh, no. So let's continue and see how it actually does the trick. So I'm on slide 56. So this is another example. I'm just taken where the loop that we are considering is a no dependency loop. Right? It has no dependency. The first example that we had shown. See. And here are some basic assumptions that the load will take 2 cycles. It will stall for 1 cycle. A floating point ALU will take 4 cycles. It will stall. There are some stall figures given, which we will use, but these are all hypothetical. It's not that precisely we are following a processor. What is significant is we assume that there is 1 branch delay slot available. So let's see what is the code that will normally be generated from this for this loop. So L.D is load. So you are loading. You'll have to load the value of this xi. So you are loading this value with reference to R1. You can see that it starts at 1000 and goes down to 1. So since it starts at 1000 and goes down to 1, so the inherent assumption here is R1 has that last element pointer already computed in it. So that those details are not being shown. So you are directly accessing that element, adding 0 to it. And you take that into F0. The resistor F0. Now, then then what will you do with this F0? You will add this value S, which is also assumed that it's a loop invariant. It is already computed and stored in F2. Right? So you have F0 plus F2, and you put that in a third resistor F4, which is the result, which is the new value of xi. Therefore, then you'll have to store that result. So F4 will be stored to 0R1, the address of Xi in the memory. Once that has been done, then you have to decrement I by 1. And you can see that after our discussions on derived iteration variables and so on, that here just the address pointer itself can be the iteration variable. And when I changes by 1, reduces by 1, assuming that this is a floating point value array having 8 bytes as a size, that index will reduce by 8. Right. So what you do, you add -8 to R1, which is an immediate addressing, and that is the new value of R1. Once that is done, then you have to compare if it is time to terminate. Right. So again, R2 is considered another constant computed, which is 0. So you check whether by doing this, R1 has become equal to R2 or not. So branch not equal to, if they are not equal, you have to continue the iteration and you go back. And for filling up, we just have a NOP here in the GDS route. Now this code certainly will not work through our pipeline. So here is a schedule. So I have a load. So I have a 1 cycle stall. So stall there. I have after that I have add. I will stall twice for 2 cycles because particularly F2 is an available constant. Then I will have a store for the result, and then I have the decrement. I don't need a stall after the store because it will happen independently once R1 has been read at the initial point. Then I will have this decrement, which will stall for 1 cycle, integer arithmetic. So it's 1 cycle. And then I will have the branch, and it will have to branch to loop, so it will stall again. Right? So this is what I get if I put the actual the different hazards into perspective and use stalling to make the code correct. So how many cycles we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 10 cycles, of which in 5 cycles I'm stalling. Not a very good scenario, of course. Okay? So let's see how we can, how we can benefit by doing some kind of, movement of the instructions to perform better. So this is the instruction generated. Okay? Now you can see here, if I have to take after the load there is a stall. If I have to utilize this cycle, obviously add is not possible. Store is obviously not possible, but I can make use of this decrementing R1. I can put that here. This will create a new constraint because now later on, if I put this decrement above add, that is before the store, the store will need to make use of this R1. So I do something smart. I put it here, and in the store, instead of doing a 0 offset from R1, I know that R1 has been decremented by 8. So I do a 8 offset from R1. That ensures correctness. But 1 stall cycle is utilized. So naturally, add comes automatically after that. And I need 2 stalls before the store. So what I do, for one of those stalls, I make use, there are 2 things being done together. very smart way. One is I'm putting this branch after this stall, after one stall, right? Because this branch has no further dependency now. It can be computed. And in the delay slot after the branch, I'm scheduling the store. So we benefit in two ways. One is the delay before the one stall before the store is utilized by the branch, and the other is the delay slot is exploited by the store so that the stall after the branch is also not necessary. And as I have already moved the decrementation of R1 above, the stall between this decrementation and branch is obviously disappeared. So you can see that out of the 5 stalls, 4 have been removed. So I have a 6 cycle schedule now for this, which is certainly much better than a 10 cycle schedule. Okay. So now in this, let us make some more observation that, say, if we look into the loop, the meat of the loop, what are the actual work? The actual work is load the value xi, add s, store it back. So this load, add, and store are the actual computation that I want. This dadd ui and bne are basically overhead instructions. They are for the management of the loop. They are for bookkeeping. Right? So here, as you can see, that for every 3 instructions in an iteration, I have 2 instructions of overhead. Right? So it's quite a lot of overhead. I mean, I have 67% additional overhead. So the best I can ask for, since my workload is 3 instructions, the best I can ask for is, can I get the execution time to 3 cycles per iteration? It would be a little ambitious, because if I can get it to 3 cycles per iteration, that would mean that I have 0 overhead. But let's see. I mean, it's not bad to be ambitious. So how do I get there? I'm just talking about the intuition. How do I get to the intuition that I have actual work of 3 instructions and my target is to have 3 cycles? The penalty that I'm getting here is the loop overhead, the 2 instructions. Now, if I unfold the loop, that is, if I make the iterations bigger, say if I unfold it once, then I'll have 6 instructions and 2 for the loop overhead still. Right. So in terms of 6 instructions, I will have an overhead of 2 instructions, which is a reduction by 50%. From 67%, I'm going down to 33%. What if I unroll it 3 times? I'll have 9 workload and 2 overhead. Okay. So that will come to somewhere around 22% or something. What if I unroll it 4 times? I'll have 12 workload instructions and 2 overhead instructions. Okay. So that is the basic idea, that as I unroll the loop more, per iteration, the overhead goes down, provided, of course, provided that I can manage the stalls by the unrolled instructions. Right? So let us try to do that. So we start with the target of having a 4-fold unrolling. So we have load, add, store, load, add, store, load, add, store, load, add, store. And to keep all of them independent of each other, I have used different resistors. You may ask, why do I need different resistors? Because they are happening sequentially. The reason I need different resistors is, if they are sharing the register. Suppose this is the first one is using F0 and F4. Second one is using F6 and F8. If it had also used F0 and F4, then I would have some kind of anti-dependency coming in. Okay? So which I want to avoid. So I assume that there are registers available to me, and the need for doing the decrement here, DI/DY, is taken care of by hard coding the offset in the load and the store. So you can see that it's logically correct. After this 4, then I do the decrement. I have already done 4 iterations. Every iteration should decrement the pointer by 8. So I decrement here by 4 times 8, 32. And then I do. Now, this is what is my wish list. Now, naturally, I will not be, it will be stupid to count that I have 12 workload instructions and 2 overhead instructions, 14 instructions. I'm done. No, it's not, because there will be stalls after the load, after the add, and so on. All these will happen. So we have to consider that. Next one. So I analyze that I have all these, and all of them are independent. All these workload instructions are independent so far as their registers are concerned. So they're independent in terms of iterations across the loop. So they do not have loop. If I share the register, then they are not, they cannot be done in parallel. They are not parallel. So you can see that there's a different sense of parallelism which is coming here. So what I see that after this LD, I need a stall for the add. So I utilize that by doing the next LD. So I bring in this LD here. Similarly, after this LD, I will need a stall. So I bring the next LD here. And this way, all 4 LDs I do first. So it is a different sense of parallelism that is going on. I've actually started 4 iterations of the loop at the same time. And I'm being able to do this because the loop is parallel. It does not have loop carried dependency. Now, after all these 4 loads have happened, there's enough cycle passed after the initial load. So I start doing the add. I do the 4 adds. I do not need any stalling between them because all values are already in that order. They're already computed and in the register. Once this is done, then I know that after computing F4 and F8, 2 cycles have already passed. So I can immediately have the first 2 stores done here without any stall. Okay. Then I need to make sure that I will have to do this adjustment also. I have to change my loop iteration by 32, and based on that the branch will happen. So there is a stall between them. So I need the DAD UI and BNE to be separated because there is a stall hidden here. So that stall will have to be exploited. So I take the 3rd store and put that into that stall slot to make use of that stalling. So I don't need that stalling anymore. I know after BNE, I have a free pass. I have a delay slot. I use that for doing the 4th one, the 4th store. If you look at this now, this whole sequence of instructions have no stall. And I have 4 load, 4 add, 4 store, 12 workload instructions, and 2 overhead instructions, 14 instructions, 14 executed in 14 cycles. Okay? So every cycle now in this modified unrolled loop cycle, every iteration will mean 4 iterations of the original loop, right? So if you divide 14 by 4, you get 3.5 cycles per iteration. Naturally, there is a trade-off. I mean, you can think that, okay, now that we have been able to do this, and the stall and all those are taken care of. So we can do better if we unroll even larger. So there is a trade-off on that significantly because of the number of independent resistors that you are using. You can try to, again, after having done this, you can try to again minimize resistors if you can. So there are a lot of other factors, optimizations will come in, but the basic idea to show was that by unrolling, by first, making sure that the loop is parallel. In this given example, I did not have to do that because it did not have any dependency at all. But by initial, if it had loop carried dependency, then I'll first make it parallel and then go through this kind of a process to get the overhead of loop management minimized to a great extent and reach almost the optimal value of 3 cycles of the original iteration. So that is the power of loop unrolling. Obviously, it is not a trivial process. It needs to be automated by determining the dependencies across iteration, and then determine if unrolling will help and compute. You can, if I go back to the slide, you can see that this offset computations had to be done with a lot of care, because here it is hard explicit in terms of the constant. So is in this store. Then you have done this DAD UI. So it has changed by 32. So you have to bring it up by 16. Otherwise, originally it was minus 16. It will be up by 16. And then here it will be up by 8. So all these, address adjustments will have to be done. And so this will, and by using additional registers, we have been able to eliminate the name dependencies, which we may again try to optimize. So let me stop here. This was the way to show how loop unrolling can significantly improve the generation of the code in terms of pipeline architecture. If there is any question, then I can answer. Otherwise, we will meet in the class tomorrow. Okay, I think there is no question and it is already time. So let us have a good day, and we'll meet tomorrow morning and close on this.